All right, so we are back. How's everybody doing today? Let's see, you got 6 of us online with us. Hopefully you guys all doing well. Let's go ahead. Just gonna set this up here for you guys. Hopefully everybody here is healthy and well, staying safe. Staying at home or going outside and staying far away from other people. Make sure you guys don't go into any kind of public places or all that kind of stuff. But how's everybody doing today? Let's see. I have got something else on here and I need to turn off. Let me see. Where is it? Ah, there it is. Okay. So, all right, April Fool's Day. Ah, that's right. Today is April 1st, which is great. April Fool's Day is just not quite the same when you're at home and you have nobody to trick but like the people in your house. And I suppose you could try to trick me or you could try to trick each other online, but it's not quite the same. Anyway, here we are, another April Fool's Day together. If we were at April Fool's together last year, don't know whether we were. Anyway, so let's just talk about, last time we were talking about acids and bases, and I gave you guys some, and I hope you guys actually did the assignment. I gave you guys some videos to watch or articles to read, which were all really about science and logs, and I hope you guys actually did that. I unfortunately don't have any videos at all on that kind of stuff. In the future, I would like to make one or two and talk about things like that. You've got, you guys saw or read some stuff on the Richter scale. You guys read some stuff on the decibel scale. And today we're going to be talking about pH. And I believe you probably already read a little bit or learned a little bit about pH. But today we're going to be jumping in and calculating pH, understanding really what it means. Because I know you guys have probably learned about pH before and you think it's some kind of scale from 0 to 14 or 1 to 14. And you got the acids and the bases on there somewhere. But we want to talk about what pH really is. Like in terms of the definition of pH, in terms of how to calculate it. We're going to jump right into that today. Okay? But I want to first, before we do that, I want to just get back to what we were talking about last time. We almost finished the homework last time talking about that, and I just want to finish that up today before we start the new stuff. So here we are. All right, so last time, again, we were talking about this, and number 10 of the whole questions from last time, probably number 10 is going to be the most important in terms of making sure you get this. Obviously, it's all important, all those other terms, but this one is probably a challenging type problem, and you need to make sure you're able to do those kinds of problems for whenever we have a test on this stuff. Okay? And maybe we should have a quiz soon, but I'm so far behind in grading that I don't feel like giving any quizzes. So sorry about that. Maybe you guys want a quiz. Anyway, let's just get right down to the stuff that we left off. We talked about amphoteric really quickly at the end, saying amphoteric basically means something can act as an acid and a base. And it depends, obviously, what it's going to react with. And so we talked about how water, H2O, can act as an acid or a base. It can either give an H plus or it can receive an H plus, okay? And that's fairly straightforward in the way that it does that, right? So water itself, if you have, let's say you have an acid, HCl, and reacts with water, H2O, and you're going to make what? You're going to make H3O plus Cl minus. In this case, HCl is acting as the acid and H2O is acting as the base, okay? And so water is receiving the H plus, turning into H3O plus. Here is the conjugate acid and here is your base. Or alternatively, we could have H2O that acts as an acid, and we see that right up here in this example where NH3 is acting as a base. It's receiving the H plus from water. Water is the acid and OH minus is water's conjugate base. Okay? And so we can see water can act in a way that is amphoteric. It can act either as an acid or a base. Let's label this one This is a base, okay? And a lot of other things can too. NH3 can act as either an acid or a base, okay? And even some other things that we have up here can act as both acids and bases. So actually a lot of things are amphoteric, okay? Not everything, but a lot of things are amphoteric just depending on their circumstances, okay? So some things, so for example, nitric acid is typically not amphoteric, but it can be, right? Nitric acid, when you mix it with sulfuric acid, can act as a base. And so nitric acid itself is amphoteric. All right, so down here to Lewis acids and bases, we are not going to focus on this. This is not going to be a big part of what we're learning. We are going to focus on the whole Bronsted-Lowry definition of acids and bases. But Lewis acids are one thing that I do want you to know about, okay? But we're not going to need to get into a whole lot of detail. So Lewis acid, so Lewis came up with a third, more or less a third definition of acids and bases, which is still important today because it's got to do with reactivity. And Lewis said, well, why does everything have to be defined in terms of H+, right? H+, what's so special about H+? Why does H+ have to be the only acid? And why does everything have to do with H+? And say, okay, H+ is so special because what? Because it wants electrons, okay? And it really wants electrons. So H+ itself is what? It's something that wants electrons because it's so highly positively charged, right? This got this really, really small positively charged thing, just simply a proton, and so it wants to be with anything that's negatively charged, so it wants electrons. And so Lewis said because of that, we're going to redefine an acid and say an acid is an electron acceptor, or something that wants electrons, or something that can receive electrons, okay? And then bases then are just the opposite, okay? A base is going to be an electron donor. And we could think of this, and it could get very easily confused and say, oh, okay, this is just some sort of redox thing, but that's not correct. This is not redox. We don't have something that's transferring electron from one thing to another thing, okay? Yeah, I'll reply to emails in time. Again, I'm a little bit bogged down, but I'll get to it, Athena. All right, so over here. So an acid is an electron acceptor, a base is an electron donor, but this is not an electron transfer. This is not redox. Nothing is being oxidized. Nothing is being reduced. It's just sort of something sticking to something else, okay? And so when you see, for example, let's just stick with the H+ example. When you see water, okay, O with two H's, okay? When you see water, water has 4 non-bonding electrons, and H+ has, well, no electrons, and it wants electrons, okay? And so what can happen is that this H2O can interact with that H+, and they can form a new bond, but it's not any kind of redox situation, right? And so they go O, H, 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 and you still have this lone pair, all right? And this whole thing is positively charged, okay? So this is a Lewis acid, Lewis base type reaction. What's going on is water is acting as a Lewis base, and it's donating electrons to hydrogen to form a bond. The electrons are being used to form a bond. The electrons are not being transferred. We're not talking about electron transfer, but we're just talking about electrons being used as a bond. They're being shared between oxygen and hydrogen here. And that's what is always going on in a Lewis acid, Lewis base situation. You have two things that are sharing electrons. And I believe if you look at the book, the situation that they give, it might, I don't remember exactly, but I think it's going to be your NH3, right, which is acting as a Lewis base, and BH3, or BF3 is even better, but let's just make it BH3. And we've seen boron a lot of times is a non-octet element, right? So boron doesn't always get an octet. It's a little bit unhappy. But hey, if you take borane or boron trihydride and mix it with ammonia, well, the two of them will be like, oh, hey, ammonia's like, oh, I've got an extra lone pair of electrons. And boron here is like, oh, hey, I need some electrons because I don't have an octet. It's a non-octet molecule there, right? Boron has only 6 valence electrons. And what can happen is that this nitrogen can then donate its electrons to boron. Now, again, this is not an electron transfer. Not an electron transfer. Instead, they're just going to use that to form a bond. And I'll draw it right up here. All it is N, H, 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 forming a bond with B, H, H, H. Now that is a real bond, and it's considered a Lewis acid-Lewis base bond, but it's similar a lot in some ways to a covalent bond, except that when you break it, it's going to break back to this way, and nitrogen's going to get all the electrons and boron's going to be left over here. Okay, so in reality, it's really just a normal bond. And this Lewis acid-Lewis base thing going on is not a transfer of electrons, but the sharing of electrons similar to a covalent bond. And you have the Lewis base is donating electrons to the Lewis acid in a sharing type fashion. Okay? And the bond between OH, and so yeah, same thing, exactly the same thing. All right, so you have a Lewis base, Lewis acid thing. Now, interestingly enough, for H3O plus, now you have 3 hydrogens, and they don't remember, which one started as an H plus. They don't remember that. Okay, so all 3 of these bonds are equivalent. They're exactly the same, and later on, when this loses an H plus, it could be this one, or this one. It could be any of those 3. So there's an equivalence there. A little bit different here. When this one, when this bond breaks, it's going to come back to exactly this and this. However, when this bond, when one of these bonds breaks, it could be any 3 of those hydrogens, and there's an equivalence there. Okay, so I want you guys to be able to know what a Lewis acid and Lewis base are. I want you guys to be able to identify them, and always keep in mind that this is not redox, okay? Not redox. There's no transfer of electrons. It's just a sharing of electrons. Essentially, your Lewis base is sharing 2 electrons with the Lewis acid. Okay, so I want to go ahead and move on from here. If you guys have any questions about Lewis acids or Lewis bases, you can ask right there in the comment section. But I want to go ahead and jump into the new stuff and spend a lot of time on the new stuff today. We're going to go over half of your homework today together, and then I'll let you guys do the other half for homework, okay? But today our real focus is on pH. All right, and I want to think about pH. So I know you guys have already read about that. Now here is a question. If there are 4 hydrogens, is it still positive? Yes. If there are 4 hydrogens, it is still positive. Now that is going to be very, very rare. And you could, I suppose, in theory, make something that has 4 hydrogens and it's not positive. In theory, a lot of things are possible in theory. But if this thing were to react with another H plus, which it can because there is a little another lone pair there, then that would look something like this. It would be O, H, 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 and the whole thing would have a positive 2 charge. Now this is going to be extremely rare and extremely difficult to make. I don't know whether it's been made before or not. We could maybe look it up somewhere. It's certainly theoretically possible, but maybe because there are some super powerful acids like magic acid and some other kinds of super acids, and maybe, just maybe, they could actually do this. I would bet that they could, but I'm not sure. Anyway, moving on from there. Let's talk today about pH. That's the whole goal. Your one main goal today is to understand what in the world is pH, and not just from a middle school perspective, but from a real high school perspective, and to be able to calculate it. Okay? Because I know you guys have learned about pH before, all right? And that's fine. It's good to have that background knowledge of pH has got something to do with how acidic or how basic something is. And you guys probably already know what neutral pH is, right? What is neutral pH, if I were to ask you? So let's see. Neutral pH is what? Anybody? Yes, 7, right? So you guys should already know that. That's kind of basic knowledge. It's your middle school kind of chemistry knowledge. And then let's see a little bit further. If we could do this, acidic pH is what, and basic pH is what? Again, I'm still thinking this is kind of like the middle school level. So acidic pH should be low pH or less than 7. Basic pH is going to be more than 7. All right, and that's kind of where your middle school pH ends there. All right, and so I've got some numbers 0 and 14, so they're kind of on the very acidic or very basic ends, right, 0 to 14. But we're going to learn that this scale is not simply 0 to 14. All right, it is not simply 0 to 14. Well, what do I mean by that? Let's get rid of this. I mean that it is possible to have a pH of, let's say, -1. In fact, that's very easy to achieve. It is possible to have a pH of 15, right? Those things are possibilities, okay? So this part of what you learned before in middle school, this is good, okay? This part that tells you it's a scale from 0 to 14, that's wrong. So you have to unlearn that, all right? It is possible to have any number of pH, okay? At least theoretically speaking, you could maybe even get down to a pH of, let's say, -2. That would be very, very hard, but it is theoretically possible, and it's very easy to get a pH of -1, okay? And a pH of 15. Piece of cake. I could do that in a minute if I were in the lab, all right? So anything you learn about that scale, it's not a fixed scale. pH is an actual calculation, okay? And so we're going to get to what that calculation means here in a minute. But before I do that, we need to go through a brief bit of background. This should be fairly easy because you guys already watched those videos. You have that one guy who's pretty cool, Eddie Wu or something like that, who talks about the whole logs. Hopefully you guys watch that. It's just like a 7 or 8 minute video about logs, which is very good because I know a lot of you guys haven't even learned about logs yet, which is sad. I wish they'd do that earlier. All right, and then here, listen, when you already did pH and the acidity of an atom calculations from pre-calc, my brain is super excited for it. Awesome, glad your brain's excited for it. So maybe you haven't done logs before, all right? And if you're in 10th grade, you probably haven't, okay? So a log is simply what? And we're gonna be doing all base 10 logs, okay? So we're gonna say that whenever we do logs here in chemistry for the whole rest of the year. Now, this is not, if you take AP chemistry, we'll also do natural logs and that kind of stuff. But anytime here for the rest of the year, when we do log of x, that's going to be log base 10 of x. So every time when I talk about log of something, it's going to be base 10. And that's exactly what your calculator does. When you look in your calculator and you see the capital L, capital O, capital G log in your calculator, that is a base 10 log, all right? It's not any old base log, it's a base 10 log, and that's what we're going to be doing. We're going to be doing all base 10 logs. So what in the world does that mean, okay? So log base 10 of something is going to be essentially the inverse of this question, right, of 10 to so let's just see, log base 10 of x equals, let's say, y. This is going to be 10 to the y equals x. So you guys should have already learned that essentially from those videos I showed you guys last time, that really log is just simply an inverse of this exponential type of formula, okay? So 10 to the answer is this thing right here. So it's kind of the inverse of this exponential, right? So you know, let's do some specific examples here. So that if we have 10 to the third, right, equals what? Equals 1,000, okay? And so what we can do is we can say log of 1,000 equals 3, all right? And we're going to be doing a lot of that kind of stuff today, mostly in your calculator, but also you should be able to do some of this stuff in your head, especially when we use scientific notation. Scientific notation makes this super, super easy, all right? So let's suppose we do something like log, and everything's log base 10 that we're going to be talking about, log of 10 to the 8th. Well, log of 10 to the 8th is simply 8, okay? And so whatever you have as the exponent here is over here. Well, why is that? Because log of 10 to the 8th is asking, okay, it's going to be 10 to what power? Well, we already know what power is 10 to the 8th. And so that makes this scientific notation super, super easy to deal with. How about log of 10 to the minus 2? Well, that's simply going to be minus 2, okay? And so what does that look like in regular notation? That's going to be log of 0.01 equals negative 2. But what that is in scientific notation, 0.01, that's 10 to the minus 2, okay? And so you got these fairly easy relationships going on here. Log base 10 is by far easier than any other logs, which is one of the reasons why we're going to start with log base 10. But secondly, it's also super, super useful in chemistry, in other science fields. All those scales that you guys looked at, whether it's the Richter scale or the pH scale or the decibel scale, they're all base 10 logs. And they're very, very useful. And so let's think about them in terms of, let's say, earthquakes or the Richter scale. Richter, I don't know. Is this I'm probably spelling that wrong. So sorry, Mr. Richter or Dr. Richter, whatever your name is. So the Richter scale, if we were looking at a Richter scale, an earthquake, we're comparing two different earthquakes, right? So one is going to be 6 and one is going to be 7. Obviously, the 7 is a more powerful earthquake than the 6, but it's not just a little bit more powerful, it's a lot more powerful, all right? And the way this is done is that this 7 essentially moves the Earth. It's 10 times more than the Richter scale number 6, okay? And in terms of power, it's even more than 10 times as powerful, but let's get to the definition. The definition of the Richter scale basically has to do with how much it moves the Earth, how large that wave is. And so it's going to be 10 times, all right? And then if you go back, all the way to, let's say, an 8 on the scale, that is now going to move the Earth. It's going to be 100 times more than the 6 on the Richter scale. It's 10 times more than 7 or 100 times more than 6, okay? And the same thing with decibels, right? The whole decibel scale, all right? It goes back to the Bell scale. It's actually, the Bell scale is a log-based scale, but the decibel scale is is 10 times the Bell scale, which is a little bit annoying. But basically, what does that mean? So if you're hearing sounds, okay, if something is, let's say, 50 decibels and something else is 60 decibels, this essentially, the 60 is going to be 10 times the sound intensity. It's not necessarily 10 times as loud, because actually your ears don't hear the intensity. Your ears might even be close to a logarithmic scale themselves, okay? But it's going to be 10 times the sound intensity or power, okay, than the 50 decibel one, okay? Or let's say you have something that's 100 decibels, all right? And then you have to just count, okay, going up from, so 5 to 6, right? This is going to be a little bit more complicated, right? So 50 to 60, that's 10 times. To 70, that's 100 times. To 80, that's 1,000 times. To 90, that's 10,000 times. And to 100, that's going to be 100,000 times the sound intensity than this 50 decibels. Okay? So same thing with the pH scale. All right? It's a log scale. Now decibels is a little bit weird because you have the zeros in front, but literally if you just deleted these zeros and looked at the Bell scale rather than decibel scale, it would be exactly the same as the Richter scale and the pH scale. Okay, so what is pH talking about? Okay, so let's talk about pH of, you have a pH of, let's say, 7 and then a pH of 5. Okay, well actually let's do 6 first. Okay, so the pH of 6 is going to be 10 times more acidic than a pH of 7. Okay, and then if you have a pH of 5, a pH of 4, okay, let's just skip down to 4. A pH of 4, so 6 is well, let's just do, this is going to be 100 times, 4 is going to be 1,000 times more acidic than a pH of 7. So each drop in 1 on the pH scale is 10 times more acidic. Each drop in 1 on the pH scale is 10 times more acidic. Or conversely, if you increase this, each increase in 1 in the pH scale is 10 times more basic, or 10 times less acidic. And you'll find that this acidity and basicity, they're just inverses of each other. And so you can talk about the basicity of something that has a low pH. You can talk about the acidity of something that has a high pH. It just has something with a high pH has a low acidity. Something that has a low pH has a low basicity and a high acidity. Okay, and so they go hand in hand, which brings us to our whole idea of, well, what is this pH scale really all about? And you guys can check out the homework as we go along. You guys should have had this on your Google Classroom, and so you can keep this as a reference. We're going to be talking about some of these. We've already answered some of these, right? So we already talked about those two, and we're going to get down to here in a second. Okay, so to understand this whole concept of acidity and basicity, we have to understand a concept known as equilibrium. And then we're going to bring that back to pH here in a minute. Okay, so equilibrium is simply, is not actually a special thing. It's a very common thing in chemistry. So equilibrium is basically the, and I'm not going to give you guys a super technical definition here. And so when we learn about it in AP chemistry or something like that later, just keep in mind that we're just learning the basics right now, and so I'll get to more precise definitions of equilibrium later, right? So equilibrium is kind of got to do with the ability of a reaction to work in both the forward and reverse directions. So technically, equilibrium is the point at which the forward and reverse directions are at the same rate, they occur at the same rate. But this whole concept of reverse and forward is probably a little bit new to you guys. And so we're going to look at one specific equilibrium. This is the only equilibrium that we care about right now. But keep in mind that this whole concept of equilibrium is very common. In fact, I'm going to say it's so common that most chemical reactions can do this. And there would be only special cases where they wouldn't be able to. Certain cases that, for whatever reason, that the reaction just doesn't have the ability to go in the reverse direction. Okay, but most reactions can do this. They can go both forward and reverse. Okay, but most of the reactions that we look at, the forward reaction is just much more favorable than the reverse direction. Okay, and so yes, you can achieve both the forward and reverse reactions for most reactions. But the one that we really, really care about is the one that's known as the auto-ionization of water. Well, what is that? That's when we take water and react it with itself. And if you wonder, well, water is always with water, that means this reaction is always occurring. And that's exactly correct. This reaction is always occurring. So when water reacts with water, it can make H3O plus and OH minus. And so water is both the acid and base towards itself, this being the conjugate acid and this being the conjugate base. And so one of those waters is receiving an H plus from the other water, all right? And you can imagine that this reaction doesn't occur very much. It's not a very favorable reaction. Water would prefer to be H2O. It doesn't like to be H3O plus and OH minus. Okay? So this reaction is not very favorable. It doesn't happen very much, but it does happen some. Okay? And so you can imagine that the forward reaction, so I've written this in a forward way, but you can imagine that the forward reaction is going to occur less than the reverse reaction. And we write this in terms of an equilibrium arrow. And so this whole concept of equilibrium, we use these kinds of arrows to do it, okay? Not this arrow, but this arrow. This is an equilibrium arrow, showing that the forward reaction works and the backward reaction works, okay? And in this case, the forward reaction only happens a little bit, and the backward reaction is going to be an easier reaction to do. It's going to happen a lot more, because this is positive and negative. They're going to want to come together and reform water and water. Okay, but this is known as the auto, just meaning auto means self, auto ionization of water. Okay, so it means it's self-ionizing. It's water that's splitting itself up, breaking its bonds and forming new bonds. It's doing it to itself. It's the auto ionization of water. Okay, auto means self. Okay, so why do we care about this? We care about this because this tells us that there's some kind of balance always going on, that the H3O plus and OH minus always need to be in some kind of a balance. Okay, and we're going to get to this, the actual balance here in a second, but let me talk about the equilibrium constant. Now I know, guys, I'm just barely hinting on complicated concepts in chemistry, but I just wanted to talk about them in terms of what it relates to acids and bases. Okay, so there's what's known as an equilibrium constant. This equilibrium constant tells us essentially how much this reaction happens, how much it favors the products and how much it favors the reactants. Okay, and this particular equilibrium constant for this reaction is 10 to the minus 14. And the equilibrium constant basically tells you essentially how much products you make versus how much reactants you make. And again, I'm not going to go through the whole derivation of why this is, but in terms of equilibrium, this must mean that the amounts of the products that we have here is H3O plus times OH minus equals a constant of this. So the product of the H3O plus times the OH minus will always equal a constant of 10 to the minus 14. Now there's a couple things I need to define here, which at first you might be wondering, like, Mr. Ketz, what in the world are these brackets? Now what is that? Okay, so brackets of something, anything, equals the molarity of that thing. Okay, so not a new term. You guys are very familiar with molarity. We've done it in 2 different units. You guys have just gotten done with doing molarity in stoichiometry. So you guys are rocket scientists on molarity. You guys are great on that, right? And so this is just a new way of drawing it, this brackets X, okay? So let's just say, so brackets OH minus means the molarity of OH minus in the solution. Okay. All right. So nothing big there. Why in the world do we do this whole bracket stuff? I'm going to get back to KW, by the way. Why in the world do we do this whole bracket stuff? The bracket stuff is just an easier way to do it. It's a shorthand. We have a lot of different shorthand stuff in chemistry, and that's it. So don't get scared about that. So what is this KW here? that is the equilibrium constant. And it's one of your questions in your homework. For the auto-ionization of water. And this equilibrium constant is basically a constant that tells you about the reaction. It tells you how much the reaction wants to happen, okay? And so if you had, and just a little background, again, you guys don't need to worry about the details of this, but if you had an equilibrium constant that was 1, okay, that would mean you should have about equal amounts of reactants and products. If you had an equilibrium constant that was a large positive, like it was a very large number, that would mean that you'd have mostly products. If you have an equilibrium constant that's much less than 1, then it means you have mostly reactants. And that's the case. So the Kw, so the auto-ionization constant for water, is 10 to the minus 14. Okay? So 10 to the minus 14 means you have mostly reactants and very little amounts of products. Okay? So now let's get on to the details of, well, what's this, why does neutral water have a pH of 7? And talk about, well, what does this mean? So we now have an equation. And this equation is true for water. This equation is true for any aqueous solution. And that's this equation, which I've already written down. Okay? This equation right here. And what is that? That is that the molarity of the H plus, or the molarity of the H3O plus, times the molarity of the OH minus concentration in any solution, any aqueous solution, is going to be 10 to the minus 14. Okay? Now, I should say that this number can change a little bit based on the temperature, but for the most part, it's going to be a constant. Okay? So, what does that mean? That means that if I increase the amount of H3O plus, if I add, let's say I have pure water and then I add some hydrochloric acid, I'm going to increase the amount of H3O plus I have in solution artificially. Okay? That means I must also decrease the amount of OH minus that I have in the solution, so that the constant of the H3O plus times the OH minus molarities will always be 10 to the minus 14. Okay? And so question here, the molarity stuff is in my channel, so you guys can watch. I have molarity made easy, and there is a video on that. So you guys can check that out if you want to know more about that. All right. So, and there is also a video, which is a little bit more of an advanced video, equilibrium made easy. But guys, that is not your level. That's not 10th grade level. That equilibrium made easy is for AP chemistry. So I wouldn't worry about that kind of stuff. But what's really cool here is this equation that we have. The molarity of the H3O plus times the molarity of OH minus is always a constant, or is always equal to this. So that's kind of the basis of how this works. And we're going to come back to using that equation here in a little bit. I want to answer first, number 4, why does neutral water have a pH of 7? And so let's use that equation to solve the neutral water. So neutral water is only water, right? Neutral water is pure water. And so for pure water, so let's just do this down here. So for neutral water, which is pure water, we haven't added any acid or base to it. We don't have anything else into it. And so we know for neutral water, and by definition, the H3O plus must equal the OH minus. Well, why? If we go back to this reaction, you cannot possibly have more of one than the other. All right? These two things, they must be the same amount. Okay? So we're going to call this number of whatever this is, we're going to call this X. Okay, fair enough. So for neutral water, our amount of H3O plus is equal to the amount of OH minus, and we're going to call that X. So we're going to go ahead and solve this equation and figure out for neutral water, what are these two numbers? Okay? So for neutral water, we have 10 to the minus 14 equals X times X, so let's just call that X squared. Okay? Simple enough. So now you can do this in your calculator, or you can do this in your head, and you can figure out, well, what is X? Okay, so you take the square root of this, try it in your calculator, or if you're familiar with square roots of exponential things, you literally just take that number, divide by 2. But let me, in case you doubt me, let's just do it in my calculator, and you can see that is the true math. And when you do some more exponential math, you'll see that it's fairly easy to do in your head. Okay, so we take the square root of, let's just do it this way, 10 to the negative 14. And oh, I don't think I need that parentheses. And I just hit enter. And I'm going to get 10 to the, so 1e negative 7, that's 10 to the negative 7. So I can solve for x. So x is 10 to the negative 7. So what does this mean? That means, oh man, my time's running out. This is crazy. This means that in a neutral water, we have a molarity of H3O plus and OH minus that equal 10 to the minus 7 moles per liter. That is your molarity. Okay, so we're halfway there. So once we know that, let me go ahead and give you guys, where did the 10 to the minus 14 come from? It is a constant. You wouldn't know that to begin with. This is a constant based on this reaction right here, okay? So that's the equilibrium constant. So let's come back over here and say, all right, now how do we get the pH of that neutral water? I need to define pH for you guys. pH is this. pH is defined as the negative log of the H plus or H3O plus molarity, okay? Equals negative log. I'm going to use these things, these H3O plus and H plus, I'm going to use them interchangeably. So it's negative log of the H plus molarity. For anything, whether it's an acid or a base, the pH is the negative log of the H plus molarity. So we can go back and we can do some calculation here. All right, so let's do the negative log of the H plus molarity. And that's going to be, and guys, you know what? I'm gonna go a little bit long here today, if you don't mind. I just want to finish up. And if you have another class, that's fine. You can just leave and come back and you just listen to the extra 10 minutes that I'm going to be talking about today. Because I don't have anything else in my next class, and so I'm just going to probably talk about 10 minutes long today. All right, because I want to go through these sample problems for you guys. All right. But this is awesome. Let's go on and talk about why is the pH of neutral water 7. So we said neutral water has this equilibrium constant of 10 to the minus 14, and we can solve, well, that means that the molarity of your H3O plus in it must be this. So for neutral water, and only, right, so for pure neutral water, we know that H3O plus molarity is 10 to the minus 7. We just solved for that, right? Now we're going to plug that into this equation for pH and calculate the pH of neutral water. So the pH is going to be negative log of this H3O plus molarity, and so that's going to be negative log of 10 to the minus 7. Well, we already know how to do logs in our heads, and you can do this in your head if you want to. We already know that the log of log of 10 to the minus 7 should be negative 7, and the negative of that is going to be 7. But let's just do it in your calculator so we can follow along. So that's going to be, the pH is negative log of what? 10 to the negative 7. And 7. pH equals 7. So it's a mathematical calculation, right? 7 was not arbitrarily chosen. All right, 7 was not saying, oh, hey, 7 is chosen because it's between 0 and 14. No, 0 and 14 are nothing. The scale is not a 0 to 14 scale, okay? pH has a mathematical definition and is not just a 0 to 14 scale. pH of neutral water is 7 because neutral water has a certain amount of H3O plus in it, naturally, always, okay? And that certain amount of H3O plus that it normally has in it is equal to the amount of OH minus that it has in it. And why? Why are they equal? Because of this auto-ionization reaction, right? The only starting point that we needed to come up with, which I didn't prove to you, is this number, this Kw. And that Kw is not something that we can derive, but is measured, right? So somebody did some measurements of water and measured this Kw. Okay? And that's beyond the scope of this course of how you would actually figure out this 10 to the minus 14. All right, I'm just going to give it to you. But just keep in mind, we have this equation for your Kw. Okay? So let's do some, I'm going to solve some of the homework problems. I know class is over right now, but I'm going to take 10 minutes to solve some homework problems for you guys so that you guys can actually do your homework. All right? And so then maybe next class we'll have a shorter class. So sorry, this is going to be a little bit longer. But hey, no class on Thursday, right? And so that's okay. That class is lasting a little bit longer today. So that, I feel like this is so cool. If you guys get this whole idea of, okay, why is pH of neutral water 7. If you get that, that's like a mind-blowing thing, if you really get that. So it's so cool, and it's such an easy calculation to do of, well, why is pH of neutral water 7, okay? So now let's actually calculate the pH of acid and base solutions, and let's just go through those. We're going to use this equation right here, for any kind of calculation for the acidity of, or for the pH of any acid solution. And this is not just some derived equation. This is the definition of pH. This is what pH is defined as. And why is it? This H, the H stands for H plus, and the P stands for power. Okay, so pH stands for the hydrogen power of a solution. Okay, so let's go ahead and calculate. And before we do the calculations, we have number 5 to deal with. You have a solution of 1 molar HCl. Is there any OH minus in the solution? All right, let's pause here. All right, number 5, you have this. Is there any OH minus? And the answer is yes. Okay, why is that? It's impossible to have 0 OH minus. Okay, because that would mean you have an infinite amount of H plus, which you don't have. Okay, and so let's make some sense of this. So we go back to this equation. This equilibrium tells us that you always have a certain amount of H0 plus and OH minus in any aqueous solution. So it's impossible to have 0 amount of OH minus, even when you have a strong acid solution. So we can even calculate that, right? So this, if you have 1 mole per liter H plus, and we know that the Kw, so 10 to the minus 14, equals your H plus times OH minus. And this HCl, that's a strong acid, and so we can approximate the amount of H plus to be 1, right? So if you have 1 mole per liter HCl, that means you have 1 mole per liter H plus, okay? So then we can go ahead and calculate the OH minus concentration. A very easy calculation, right? So it's going to be, if the H plus molarity is 1, and you don't know what the OH minus concentration is, 1 times the OH minus molarity equals 10 to the minus 14. Oh, okay, that means the OH minus molarity has got to be 10 to the minus 14 moles per liter. So it's a very small amount, but there is some there. All right? So your pH, we're going to calculate it this way for acids. Right? Your pH equals the negative log of the amount of acid you have. Right? And I'm only going to give you guys strong acids. All right? Weak acids are going to be a lot more complicated. All right? And for bases, we're going to say the pH is going to be 14 plus the log of the base molarity. Okay? And this is a derived equation, and we could work through how that works. I know you guys haven't learned about logs, so it's a little bit complicated for you guys, but it's actually fairly easy to derive from the equation that I have right over, magically appear, right over here. Okay, so basically just derive from that. Okay, so I can do that. And let me also say, I think your homework asks you to calculate the POH. I'm not sure. Does it? Let me just check, because if it doesn't, then I'm not going to worry about it. Yeah, the POH is what? The POH is going to be the negative log of your base concentration. P is going to be defined as negative log of something, okay? So P of X equals the negative log of X. So pH is the negative log of the H plus. POH is the negative log of the OH minus, all right? And then I have these two are defined, these two are your definitions of pH and POH. And this is a derived equation that I'm not going to take the time to derive for you guys, but it's basically the pH can be 14 plus the log of the base for bases. All right, so I know there's a lot of stuff, and we're going to get to this stuff and learn a lot more about this stuff next time too, okay? So let's finish up. I'm going to talk about number 7 and number 8, and we're going to do some calculations here together. Number 7 is super easy, okay? So what do? I'm going to do number 1 for you guys and number 3 for you guys, and you guys can do the rest, okay? So number 1, calculate the pH of a 10 mole per liter HCl. So what I'm going to do is the pH is the negative log of the acid molarity, which you have the acid molarity, okay? So that's going to be negative log of 10. Enter. Boom, I got my answer. That's going to be a negative 1. Yes, it is possible to have a negative 1 pH. Yes, in fact, you can have even smaller than that pH, okay? So 10 mole per liter HCl, definitely possible. I'm going to skip down to number 3. Number 3, that's sodium hydroxide, so that is a base, okay? That is a base, and we know that because of this OH minus right here, okay? So when I do a base, I'm going to use this equation right here. The pH is going to be 14 plus the log of 0.1. And that's going to be 13. Okay? And you guys can do the other ones and see what numbers you come up with for those. That's fairly easy when I give you the molarity. Let's end today with one difficult problem, and I'll see what you guys come up with for next time. Okay? So if I finally do number 8, all right, we've got sodium hydroxide, and I've got a 250 milliliter aqueous solution, all right? And I'm going to go through this fairly quickly, and you guys can, do your best to follow along. All right, so we have 10 grams of sodium hydroxide, and that means because we have grams, we need to figure out the molarity, because everything's defined in terms of molarity for these things. So we need to figure out the molar mass of sodium hydroxide. That's simply going to be sodium plus oxygen plus hydrogen, which is approximately 40, but let me just get the actual true number here, okay? So that's going to be sodium, which is 22.99, plus oxygen, which we know is 15.999, and plus hydrogen, which is 1.0079, and that's going to be 39.997. We'll just round it off to that, okay? 39.997 grams per mole. Okay, so now we can do some calculations. We want to get the molarity of this solution, okay? So what I'm going to do is I'm going to take my 10 grams of sodium hydroxide, and I need to convert that to moles. So I'm going to use the molar mass to do this. If I start with grams, I need grams on the bottom. That's going to be 39.997 grams is 1 mole of sodium hydroxide. Okay? So that's going to be 10 divided by 39.997. And that's going to be a nice number. Okay? So 0.250 moles of NaOH. All right. Now we have a solution. It's 250 milliliter solution. Okay, that 250 milliliter solution is the total volume. And we know that molarity is number of moles over the volume. And I literally could have done this as a conversion factor too, but I'm going to do it this way instead. So molarity is moles over the volume. And so we have 0.250 moles divided by the volume, 250 milliliters. You have to convert that to liters. So that's going to be 0.250 liters. Oh, this is so nice. Look at this. The math just works out so well for this one, right? So 0.250 divided by 0.250 equals 1.00 moles per liter. So we have a 1 molar or 1 mole per liter solution of sodium hydroxide. Now that we know the concentration or the molarity of sodium hydroxide, we can go ahead and calculate these different things. So it says, what is the OH minus molarity? That's this. So if the sodium hydroxide is 1 mole per liter, then the OH minus molarity must be 1 mole per liter. What is the H plus molarity? Now, we talked about this before. We said your OH minus times your H plus are going to equal 10 to the minus 14. So if this is 1 and this times this is 10 to the minus 14, so we just substitute 1 in there for OH minus, your H plus must simply be 10 to the minus 14. Okay? Finally, what's the POH and what's the pH? So the POH is the negative log of the OH minus molarity. And we can do that in your calculators right now. So negative log of 1. Or if you know what log of 1 is, you don't even need to do this in your calculator, right? So you're doing the negative log of the OH minus molarity. So it's negative log of 1. That is 0. Log of 1 is 0. So negative log of 1 is 0. So the POH in this case is 0. pH is going to be the negative log of the H plus molarity. Okay? So what's the H plus molarity? It's 10 to the minus 14. And you should be able to do that one in your heads too, right? So what's the log of 10 to the minus 14? And what's the negative of that? Think about that. So negative log of 10 to the negative 14. And I don't know if it's going to like my parentheses there, but anyway, whatever. Aha, it's okay. So it's 14. Okay? So the pH is 14. And so we've calculated the pH that way. You could also calculate the pH this way too. So if we calculate the pH is 14 plus the positive, so plus the log of the OH minus molarity, we can do that. It's going to work out to be exactly the same thing. Let's try it out. You don't have to do this, but I just want to verify this. I want you to see how this works out. So 14 plus the log of the OH minus molarity, which is 1. Well, we already know log of 1 is 0, right? But let's check it out. 14 plus the log of 1 is 14. So whether you do your calculation this way or do the calculation this way, the pH is the same, right? In both cases, the pH is the same, and it should be. Notice also something else very, very interesting. All right, and this is also going to be by definition, but notice that the POH plus the pH is 14, and that's always the case. POH plus pH is 14, all right? And that's kind of where this whole calculation came in from, all right? So that's it. I know it's a lot today, but you guys have off tomorrow, so no class on Thursday. We'll come back and talk about this on Friday, and there's nothing new down here. So it's a bunch of practice. Please, please, guys, go through these practice problems. And I know this is going to be one of your hardest assignments, this particular unit, but you can do it. Go through it. Do your best. You got 2 days to work on it. And peace, guys. I'm going to take off now. All right. See ya.